Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 29th lecture. In this lecture, we will be discussing power analysis. In the earlier lectures, we have discussed various design tasks, and these tasks were related primarily to the area and the timing of the circuit. However, a third figure of merit, that is power, is also very important for our circuit, and we need to consider that in VLSI design flow. So, the tasks that we carried out in VLSI design flow that are related to power can be broadly classified into two categories. The first one is related to power analysis, and the second one is related to power optimization. So, in this lecture, we will be discussing power analysis, and in the next lecture, we will be discussing power optimization. Specifically, in this lecture, we will be discussing various components of power dissipation, power models which are there in the technology libraries, and the techniques to estimate power dissipation. So, the power dissipation in a CMOS circuit can be broadly classified into two types. The first one is dynamic power dissipation. So, dynamic power dissipation occurs when a circuit performs computation actively, meaning that in a circuit the signals are basically changing. So, it may be say a signal or a net whose value is changing from 0 to 1 or 1 to 0, or there is some gate, a logic gate, and its output is toggling maybe from 0 to 1 or 1 to 0. So, whenever there are changes in the signal values or the output of the gate is changing, then we say that our circuit is performing computation actively, and the power that is dissipated during this active computation, that is known as dynamic power dissipation. The second type of power dissipation is known as static power dissipation, and static power dissipation occurs when the circuit is powered on, means that the circuit is connected to VDD and ground rails, but it does not perform active computation, meaning that the value of the signal is not changing. For example, suppose there is an inverter. Now, this inverter is connected to the VDD line, right, VDD line and the ground line, right. So, we are connecting this inverter to the power supply, but suppose the value of the input net and the output net, these are not toggling, it was held constant. Suppose the input was held constant at 0 and the output was held the inverter will produce an output 1 in this case, and these signals are not changing, the input and the output values are not changing, then the power which will be dissipated by this inverter, that is the static power dissipation. While if there is an inverter, right, and it is of course connected to VDD and ground, and suppose the input is making a transition from 0 to 1, right. So, if the input is changing, the output will change, right. Input is changing from 0 to 1, output will change from 1 to 0, right. So, the power which will be dissipated in this case, this will be known as the dynamic power dissipation. Okay. Now, let us discuss this, or let us look into this dynamic power dissipation and static power dissipation in more detail. So, let us consider an inverter. This is an inverter which is a CMOS inverter, which is driving say M loads, right. So, we have the loads are defined as C, this load, this is another load pin and so on, and there are M load pins, and each load pin is showing an input capacitance as C Ci. So, this is C1, this is C2, these are input capacitances of the pins, right, which are driven by this inverter, right. And suppose it is driving these loads through a wire, and wire also has a capacitance, a ground capacitance, which is, we say that Cw is the ground capacitance. Additionally, let us assume that this inverter, the CMOS inverter that is here, right, this has also got some internal capacitances, for example, drain diffusion capacitances, which can be considered as the connected to the output node Z, right. So, that is represented as CD, right. So, these are the various components of the capacitances which will be charged and discharged as the input of the inverter is changing. Suppose, say, the input changes from 0 to 1, right, then the output will change from 1 to 0, right. The output at this point will change to 1 to 0. And while this this transition is happening, the capacitance C1, C2, Ci to Cm, all these capacitances will be getting discharged, right, because when it was 1, it was charged to VDD, now it is coming to 0, so it will be discharged. Similarly, Cw will be discharged and Cd will be discharged, right. And if the transition is from, say, input at the input, the transition is from 1 to 0, then the output will transition from 0 to 1, right. So, in this case, all these capacitance CD, Cw and all the pin loads, right, pin load capacitances, those will be charged to VDD, right. So, when the inverter is this blue inverter which is shown here, if it is making a transition, all the capacitors will be charged and discharged, and during this charging discharging, there will be some power dissipation which will be dissipated in this process, and that power dissipation is known as switching power dissipation, right. Now, let us understand that how to quantify this switching power dissipation. Now, to quantify this switching power dissipation, we need to consider the internal details of this inverter, right. So, if it is a CMOS inverter, this CMOS inverter, internally it consists of a P MOSFET, which is shown here, and an N MOSFET, right. And these PMOS and NMOS acts as a switch, right. So, whenever the input is, say, 0, right, then the PMOS will be turned on and this one will be, the NMOS will be switched off. Similarly, if the input is held at 1, right, the PMOS will be turned off while the NMOS will be turned on, right. So, and if we consider all the load capacitances, right. So, there were 3 components, one is CD, then Cw and all the pin load, right. So, let us assume that the combined effect of all these pin loads is Ci. So, let us define Ci is equal to summation of Ci, I is equal to 1 to m. There are m loads. So, I to m. Let us define this. Then we can say that Cl is equal to Cd, that is internal capacitance, drain diffusion capacitances or capacitances associated with the output node Z, right, Cd, plus Cw, that is the wire capacitance or interconnect capacitance, and Ci, that is the combined effect of all the pin loads. So, we can represent this circuit, this circuit using this transistor level circuit, right. So, we have replaced this inverter with the PMOS and NMOS implementation, and we have replaced all the load capacitances with a load capacitance Cl, which is the sum of Cd plus Cw and Ci, right. Now, in this circuit, this circuit that we are considering, whenever a transition happens, say, from 0 to 1, right, suppose the transition happens from 0 to 1 or 1 to 0, these loads, the Cl will be charged and discharged, right. So, suppose if it was the transition was happening from 1 to 0 at the input, right, in 1 to 0 at the input, the transition at the output Z will be from 0 to 1, right, 0 to 1. So, whenever a 0 to 1 transition happens, this node Vz, that will be charging to VDD, right, through this path, right, this through this through. So, this transition, whenever the input V A is equal to 0, this PMOS will be turned on, and that will charge it to, that will charge the CL to VDD, right. So, in this process, when the current is drawn through the PMOS, this PMOS, there are some resistances associated with the transistors and the interconnects, and those will be basically responsible for the power dissipation. So, remember that a capacitor standalone can never dissipate power, it can only be charged or discharged, but the resistances associated with this circuit, those are actually dissipating power. So, when a charge, when this CL is being charged, then the energy, so this capacitor CL will store some energy. While storing that energy, that energy, some power will be dissipated by this NMOS and the power lines and the internal resistances of the battery and so on, and that will lead to a power dissipation of half CL VDD square, right. And in the next cycle, when the transition happens from 0 to 1, this stored energy in the CL, in the load CL, that gets dissipated through the NMOS. So, whenever a transition happens from 0 to 1, 1 is whenever the input is 1, the NMOS gets switched on, right. So, there is a path from Vz to the ground, and through that path, whatever the charge is on CL, that will be dissipated. So, whenever, and in this, so the half CL VDD square, which was stored in the capacitor, that will get discharged in the second half of the cycle. So, whenever a transition happens from 0 to 1 to 1 to 0, one complete cycle in this for this inverter, then a total of half CL VDD square plus half CL VDD square, that is CL VDD square, that much energy gets dissipated, right. So, this is the amount of energy that will be dissipated in the process of making a transition from 0 to 1 and 1 to 0 at the input of the transistor, right. Now, from this energy, how do we compute the power, right. So, we know that the energy and power are related by, the power is energy divided by time, right. So, to get the power dissipation, we need to understand that in what time this switching happened, right, in what time this switching from, or complete cycle of switching from 0 to 1 and 1 to 0 happened. If it happens very quickly, then power dissipation will be higher. If it happens slowly over a long period of time, right, from 0 stays long for 0 and then switches again from 0 to 1 after a long time, then the power dissipation will be lesser, though the energy dissipation will be equal to CL VDD square in one cycle of the transition. Now, how do we quantify power? To quantify power, typically in a synchronous circuit, what we do is that we compute power as CL VDD square alpha times FCLK. Now, we multiply it by a factor alpha FCLK to denote that in what time duration this energy was dissipated. And what is FCLK? FCLK is the frequency of the clock in the circuit, and alpha is known as the activity of the signal. Now, we have defined alpha such that the time needed for this energy dissipation, or the time interval in this energy dissipation, is captured correctly by the suitable definition of alpha. And how do we define alpha? We define alpha is equal to 1 when the output completes one cycle of transition in one clock period, right? Meaning that, suppose let us say that this power dissipation was happening in one clock cycle, right, which in this suppose there is a clock signal, right, there is a clock signal whose time period is t, right, and the FCLK is equal to 1 by t, right. And let us assume that in this time interval this much energy is SW was dissipated. So, what will be the power in this case? The power in this case will be P is equal to energy dissipated, that is CL VDD square, right, divided by the time interval, that is T, right. Now, 1 by T is FCLK, right. So, CL is times VDD square into FCLK, that is what the power dissipation is if the transition, if the output node Z was transitioning or doing a complete transition from 0 to 1 and 1 to 0 in one clock period, right. Now, what happens in a synchronous circuit, that is that the output node, for example, this node Z will not toggle every clock cycle, right. It will toggle say once in 5 clock cycles, right. So, if that happens, then this alpha will scale that, right. If say this 0 to 1 and 1 to 0 transition happens once every 5 clock cycle, then alpha will be taken as 1 divided by 5, that is 0.2, right. So, alpha is a way of capturing what is the activity of the node Z, meaning that how quickly it is transitioning or how frequently it is transitioning within a clock period, right. So, this is this formula PSW is equal to CL VDD square alpha FCLK is known as the switching power, that is it quantifies the switching power of the inverter. For other types of circuit, for example, the other type of logic gates, such for example AND gate, OR gate and so on, a similar formula can be considered where the CL can change, alpha can change, and FCLK will be based on the circuit, right. So, this is the general formula for a node, that in this case Z, transitioning with an activity of alpha. Now, there is another type of power dissipation which is known as short circuit power dissipation. And what is short circuit power dissipation? So, short circuit power dissipation occurs if the input is transitioning at a slower rate, right, which is if the input is say rising at say from 0 to 1 at a slower rate, then what will happen is that for some small amount of time this transistor PMOS and this NMOS both will be switched on, and there will be there is a path from VDD to the ground through this switched on transistor. Though this time interval will be very small, still there is some small time interval when there is a direct path from VDD to the ground. And when this kind of path becomes more frequent, which becomes more frequent if the transition of if the transition or at the input is slower. If we decrease the transition, if we increase the slew, right, then it means that the transition is happening slowly, and in that case the time interval for which there will be a direct path from VDD to ground, that will be increasing, and during this time, whenever there is a direct path between VDD to ground, during that time the power that is dissipated, that is known as short circuit power, right. So, we can quantify short circuit power as VDD into ISC. VDD is the supply voltage and ISC is the short circuit current, right, whatever the short circuit current which is flowing from VDD to ground, right. So, now if we look into the dynamic power dissipation, there are two components. One that we saw in the previous slide, that was related to switching and the charging and discharging of the load capacitances, right, and the other one due to the short circuit of or short circuit path from the VDD to the ground line, and therefore, the total dynamic power dissipated by a circuit is the sum of these two components. Now, let us look into the static power dissipation. So, static power dissipation occurs when the inputs and when the signal is held constant. For example, suppose this signal input was held at constant 0 and the output will be for an inverter, the output will be 1, right. So, whenever this input is 0, right, we say that the PMOS will get turned on, this will be switched on, right, and there will be a direct path from there will be path, low resistance path from this point to this point, and this transistor will get charged to CL. Once that transition, charging of these load capacitances CL has happened, when the CL is completely charged, then no more current is drawn from this VDD, right, from the power source, and the current should ideally become 0. And whenever the input is 0, this NMOS will be switched off, right. So, ideally, if this is switched off and this current also dies down after charging, then what we expect that in the stable state, meaning that whenever the input value is not changing, in that case there will be no current flowing through these transistors, and no power dissipation will happen. But in reality, what happens is that whenever we say that, for example, whenever the input is 0, this transistor, which we assumed it to be completely switched off, they do not get it completely switched off. They leak some current, the current between, say, this point to this point, because of various reasons. So, what are the reasons why there can be some current from this path to this path, right? Whenever this is leaking current, right, this, for example, when the input is 0, this transistor will be leaking current, and its value is, say, I leak, right. So, whenever the input is 0, this PMOS is already turned on, right. So, there is a path from VDD to node Z through a low resistance, right. So, the current that will be decided, I leak, will be decided by this switched off transistor, right. If this switched off transistor was an ideal one, in that case I leak would have been 0 and static power dissipation would have been 0. But because of various reasons, this I leak is appreciable. At advanced technology nodes, this has become significantly larger. And why this I leak exists? There are a few reasons. The first one is subthreshold current, right. So, when we say that when the transistor is when we put the gate voltage of a transistor below, say, threshold voltage, ideally we expect that the transistor is completely switched off, right, for an NMOS case, right. But however, whenever the transistor is whenever the gate voltage of a transistor is below threshold voltage, there are some electrons which are having high energy, and they can go from the drain to the source, right, from this drain to the source. So, those high energetic electrons contribute to this subthreshold current. Additionally, there can be some gate leakage through the tunneling path, right. There can be some gate leakage. So, between the gate and the source and drain, there is a insulator and there is a capacitor. Ideally, no current should flow through that, but because of the small size of the gate oxide, some tunneling current can flow from the gate to the source and drain, and they also contribute to the leakage current, right. And the third reason is the junction leakage. So, there are within the transistor, there are junctions which are reverse bias junctions, and ideally the current in a reverse bias junction should be 0, right. But in real PN junction, those are the reverse bias current is appreciable, maybe in pico amperes or say in nano amperes, but they exist, right, and they also contribute to the leakage current. Typically in advanced technology nodes, the leakage current is dominated by the subthreshold current. And how can we quantify this power dissipation, which is dissipated in when the signals are held constant to 0 or 1? We can simply multiply the leakage current I leak with the VDD, right. VDD is the power supply voltage, right. So, we can get the static power dissipation. So, now if we want to get the complete view of the power dissipation in a CMOS circuit, so there are two types of power dissipation. The first is the dynamic power dissipation and the static power dissipation. And dynamic power dissipation is again of two types, the switching power and the short circuit power dissipation, right. So, using those the formulas that we discussed, we can compute the total power dissipated in a CMOS circuit. Now, let us look into the library models which exist in the technology libraries for modeling the power. So, first let us look into the dynamic power dissipation. Let us again consider that there is an inverter, right, this inverter which is driving M loads and their pin loads are C1 to Cm, right, and we have already computed that what is the power energy dissipated in one cycle from 0 to 1 and 1 to 0. So, that was CL into VDD square, where CL was, we have seen that we had defined CL is equal to CD, that is the drain diffusion capacitance, plus CW, that is the wire capacitance, right, the capacitance related to the wires or interconnects, plus Ci, which is the combined effect of all the pin loads, right. And the second part of the dynamic power dissipation is the short circuit power. So, let us assume that since the formula that we derived in the previous slide, it was VDD into ISC, that is the power dissipation. So, this is the short circuit power dissipation, right, VDD into ISC. Now, if we want to get the energy, we have to multiply it with time. So, let us assume that the inverter, this inverter was in the short circuit condition for the time tau SC, and during that time interval the average current that was drawn was the short circuit current that was drawn was ISC. So, this formula E dynamic is equal to CL VDD square plus VDD ISC tau SC. So, that tau SC is the time for which the short circuit is happening, right. So, this gives us the total energy consumed in 0 to 1 and 1 to 0 transition for this CMOS inverter, right. Now, if we put the value of CL, right, we get this equation, right, that this part remains the same, and instead of CL we write CD plus CW plus CI. Now, this is the total dynamic power dissipation. In this formula we can identify two different sections. The first one, we say that the components which are dissipated within this cell, right. So, there are two components of this power. So, we can identify two components of the power which is dissipated within the cell, that is this is within this blue cell, and the one which is dissipated outside, right. So, we can segregate two components based on this capacitance as value, right. So, we combine we say that the energy dissipated in charging and discharging CD, that is the drain diffusion capacitance, which is lying inside the inverter, that is the internal component, and also the short circuit power dissipation, that is also contained completely inside the inverter, right, inside the PMOS and the NMOS of the inverter, and therefore, that is an internal component. So, these two are the component of energy dissipation which is dissipated within the cell, right, and the other component Cw plus Ci, that is in charging this interconnect capacitances and the charging of this pin load C1, C2 to Cm, those are external to the inverter, and we say that it is E. So, we can write E dynamic is E internal plus E external, where E internal are these two components and E external is the third this component, right. Now, in when we try to model library, which kind of power should we model in our library? So, the power which is dissipated inside the cell, right, inside the cell meaning that is inside this inverter, that can be modeled in the library, right, because that is the property of that cell, right, and that can be computed at the time of library characterization, right. So, the energy dissipated inside a cell is the property of the cell and is modeled in the library, and the energy dissipated outside a cell, that is E external, depends on the environment or the external loads, right. It depends on the external loads and the capacitances, interconnect capacitance Cw, and these can be computed based on the instantiation of the inverter, right. So, the energy dissipated outside the cell can be computed by the tool based on the activity and the power supply and the capacitances, external capacitances at the time of power estimation, right, or power computation. However, the component of power which is lying inside the cell, that is modeled inside the library, because that is the property of the cell that we are characterizing. So, power can be estimated using energy per transition. So, these are energy numbers, right. So, using these energy numbers, we can compute the power by multiplying with the activity and the clock frequency, right. So, now let us look into that how this internal power is modeled modeled in the library. So, this internal power is modeled similar to the NLDM that we discussed earlier, and the power model that we have is known as nonlinear power model. So, the internal power dissipation depends on the output load and the input slew, and therefore, it is modeled as two-dimensional table as we did for say NLDM for the delay, right. In the delay also it was the delay was dependent on output load and input slew. Similarly, the dynamic power dissipation inside a cell, that depends on the output load and the input slew. And how do we model it? We model it using an attribute which is known as internal power, right. We have an attribute internal power in the technology library which captures the internal power dissipated inside our cell, and this model is known as nonlinear power model or NLPM. Okay. So, let us have a look at how does NLPM look like, right. So, similar to timing arc, we have power arc, we have a start pin, right, and an end pin. So, the power arc is defined at the end pin, and the related pin is the start point, right. And then we have index. The attribute is internal power, and then we have values which can be different for rise case and the fall case, and therefore, those are captured using rise underscore power. Similarly, there will be fall underscore power, and this rise underscore power is a 2D table which depends on the input net transition or input slew and the total output net capacitance or the output load, right. So, this is how the NLPM model look like, and the numbers that are represented in this table, those are the energy numbers, right. So, the values are that are shown here, those represent energy dissipated per transition. Now, to get the power dissipation, we have to multiply with the clock frequency and the activity. And how is a static power dissipation modeled in the library? Now, the static power dissipation depends on what is the static value at the pin. For example, if there is a NAND gate, right, suppose there is a NAND gate, then for the case when the input is 0 0 or the case when the input is say 0 1, the power dissipated will be different, the static power dissipated will be different. So, we model this using a when condition. So, what do we mean by when condition? Let us understand with an example. So, suppose if there is a NAND gate, so we will define leakage power as a value say 20 when not A and not B. What it means is that when A takes a value of 0 and B takes a value of 0. For let us assume that these are the pins. So, for the 0 0 case, the power dissipated is 20. Similarly, we say if A is equal to 1, right, if it is A and this is P, right, A is equal to 1 and B is equal to 0, the power dissipated in this case is 150, right. Now, in addition to the leakage power based on the when condition, an average value can be defined for a cell also. So, if the tool needs to compute, it does not know the probability of a signal being 0 or 1, in that case an average value of power dissipated by a cell is also defined by the library, and that can be used by the tools. Now, we have seen that how to compute the power, right. So, P total is equal to the switching power, right, and the short circuit power and the leakage power or static power dissipation. These are three components, right. Now, how do we estimate so given a design or given our circuit, how does a tool will compute this total power dissipation, right. So, computing power dissipation is a challenging problem. Why? The first of all, the challenge is because of this CL. Now, what is the value of this load capacitance, right? So, when we say for example, we are writing an RTL, at that time we do not have any interconnect, right. So, and we also do not know the load capacitance of the pins or the signals which will be driven, right. So, in that case the CL values cannot be estimated accurately, right. Even we have done say technology mapping. In that, after technology mapping, we know the pin loads, but we still do not know the interconnect capacitance, right. So, in that case again CL value that we are getting is not very accurate. So, what it means is that as the design flow progresses, the value of CL becomes more and more accurate as the abstraction decreases and details increases. For example, CL can be computed very accurately once we have done the routing. If we have done the final routing, then CL can be estimated very accurately, right. The other difficulty is related to the activity, right. So, the accounting for the activity of the signal is very difficult or very tricky. Why it is difficult or tricky? Because the activity of the signal depends upon the application being run, right. For example, let us assume that there is a processor that we are designing, right. Now, depending on what application is running on this with the help of this processor, right, the switching activity can be higher or lower. For example, if we are doing say video rendering, right, in that case the activity can be much higher. But if we are just editing a document, in that case maybe the activity may be lower, right. So, for a given chip or an integrated circuit, estimating the activity is very difficult because it depends on the application, and we need to understand the details and the loads that the application will need to apply on our circuit to estimate the activity of the signal. Another thing is that even we know the activity, right, we know that okay, this program will run on our integrated circuit, right. Even that in that case the logical structure and the circuit topology will decide the activity of the signal, right, and then accounting for those logical structure and the circuit topology, that may also be tricky, right. So, how does the tool estimate the activity and compute the power dissipation, right. So, there are two types of techniques. The first one is simulation based techniques or vector based techniques. So, in this technique what we do is that we perform the simulation using test bench, right. So, we have seen that when we designed say our RTL, we did the functional verification, and for doing functional verification we wrote our test bench and ran the simulator, right. So, we can use the same test bench to run the simulation, and then using the simulation result we can record the output response and save them in say VCD file, right. So, we have discussed earlier that there is a value changed dump file or VCD file in which the values can be written, right. So, in some sense this VCD file will be recording the activity of the signals, right. Now, using the VCD file we can convert into a format from which activity measures can be easily extracted by the tool. And what is that format? That format is typically switching activity interchange format or SAFE format, right. So, we did simulation, and after simulation we got VCD file, and from VCD file we get a SAFE file which is in a format from which the activity can be easily extracted by power analysis tool, and using these activities the tool will compute the power dissipation or in our circuit, right. And for some signals or sometimes we may not have the activity file. In that case the power analysis tool will typically assume some default activity, for example 0.2 for the signals, and based on that the computation power estimation can be done, right. So, this technique which is based on say simulation is known as simulation based technique or vector based techniques. The other type of technique to estimate power dissipation is probabilistic technique, and those techniques are also known as vectorless technique. In probabilistic technique what we do is that we propagate the activity through the circuit by considering the logic function of the gates encountered in the path. We assume certain activity at the inputs of our design or circuit and propagate that activity throughout our circuit using the logical structure of our design, right. So, let us assume, for example, to illustrate this, let us assume that there are two signals A and B. There are two signals A and B, and the probability of being 1 is 0.5 for A. So, there is a signal A whose probability of being 1 is 0.5, and there is another signal PB whose probability of being 1 is 0.3, right. Now, if these two signals were going to an AND gate, right. So, AND gate. So, what will be the probability of being 1 at this output, right. So, we can easily compute in this case is that if the output will be 1 only when both the inputs are 1, right. So, therefore, we can multiply 0.5 and 0.3, we get 0.15, right. That is the probability of being 1 at the output of the AND gate, right. So, if we know the probability of the signal at the input, we can using the logical structure we can compute the probability of being 1 at the output of the gate, right. Now, if these two same signals were say propagating or going to an OR gate, for example, there is an OR gate. Now, what will be the probability of being 1 in this case? So, in this case it will be easy to compute the probability of being 0, right, and then from there if we subtract from that probability from 1, then we get the probability of being 1, right. So, for the signal A the probability of being 1 is 0.5, so probability of being 0 is also 0.5, right. This is probability of being 0, right, for the signal A. Now, what is the probability of being 0 for the signal B? It is the probability of being 1 was 0.3. So, probability of being 0 for the signal B will be 0.7, right. Now, output of an OR gate will have a value 0 only if both the inputs are 0, right. So, what will be the probability of being 0 at the output of the OR gate? Probability of 0 at the output of OR gate will be 0.5 into 0.7, that is 0.35, right. Now, we can compute the probability of being 1 at the output of A plus B as 1 minus 0.35, that is 0.65, right. That is what is shown, right. So, in this case it was easy to compute because we are assuming that A and B are totally uncorrelated signals, right, those are independent signals, right. But in real designs what happens is that the signals diverge, they converge, and therefore there are correlations, right, there can be correlations, and then the computing the probabilities and other things will not be that easy, right. So, the exact computation of the or estimation of the power dissipation is not the part of this course. However, if you want to look into more detail, you can refer to these books. Now, to summarize what we have done in this lecture, we have looked into power analysis of a CMOS circuit, and then we looked into various components of power analysis, and we also looked into the library models which are used for power analysis and how activities can be estimated, right. So, in the next lecture we will be looking into that how we can change our design or how we can make modifications in our design to reduce the power dissipation. Thank you very much.